All right, we are finally to the end of chapter 5. 5.10, improper integrals, is the last section in chapter 5 in your book. So that, I guess, is kind of a big deal. It's also the last section of this subblock that I call advanced methods of integration. It's kind of the last time we'll be learning a new way to calculate an integral. And you're like, well, I thought that was the whole class. What are we going to do going forward? Going forward, we're going to kind of do some applications of what we've already learned. So we'll take our ability to calculate all these different integrals, and we'll show how that ability can be used to solve real world, maybe that should be in quotation marks, real world problems. So that's kind of the game plan for what we're doing. This chapter finishes on kind of a good note. I think improper integrals are kind of interesting just from a theoretic perspective, and they're not super hard to calculate. So it's a good little section. This will be a 2-video section. In this video, I'm going to talk about unbounded integrals, which is just one type of improper integrals. And then in the next video, I'll get into a different type of improper integral. So when I talk about an unbounded integral, what I mean is something like this, right? See if you can translate this kind of into English. What is this asking you to do? We have this function 1 over x, and what we're asked to do is find out how much area there is underneath that curve, starting at 1 and going to infinity? That's weird. I'm not used to seeing symbols like infinity up here. I'm used to seeing numbers up here. If this were a number like the number 3, this problem would be really easy. Here's a graph of y equals 1 over x. If I ask you how much area there is from 1 to 3 here, it's a really easy problem. It's something you've been doing for a few weeks now. All you'd have to do is take the antiderivative of this function. The antiderivative of 1 over x is the natural log of the absolute value of x. And then plug in 3 and plug in 1 and subtract those two. So the natural log of 3 minus the natural log of 1. And since the natural log of 1 is just 0, that tells us that this answer, how much area there is underneath this curve between 1 and 3, is just the natural log of 3. But that's not the question that we're looking at, right? The question we're looking at deals with an unbounded integral. It doesn't stop at 3. It, informally speaking, goes all the way up to infinity. So what does that mean in terms of our picture? Well, what I want to know is how much area is there to the right of 1 underneath this curve? And you'd be like, well, that's a dumb question. Like, there can't possibly be an answer to that, right? I'm going infinitely far out to the right. So there must be infinitely much area underneath this curve. And you got to be a little bit careful there. If that was your intuition, it turns out you're right. It turns out that in this specific case, there is infinitely much area to the right of 1 underneath this curve. But it's not as obvious as you might think. Weird things happen when you start dealing with infinities. I mean, we've already kind of seen it. Just the area from 1 to 3. I could make an argument that that should be, loosely speaking, infinite. And you're like, no way that's infinite. Like, it's smaller than 3 because it's smaller than this 1 by 3 rectangle. And you're right, it's not infinite. But what if I argued that the way we figure out this area is by making a whole bunch of different rectangles? And we look at the limit when n approaches infinity. So informally speaking, we have infinitely many rectangles underneath the curve here. And the area of any individual rectangle is positive, right? You can't have a rectangle with no area or negative area. So I'm adding up infinitely many positive things. Shouldn't I be getting infinity as my answer? And it turns out that kind of paradoxical thinking is what Calc 3 is all about. That you can add up infinitely many positive numbers and not get infinity as your answer. And so we get a little bit of a glimpse of that in this section. In this specific example, the area to the right of 1 underneath this curve is infinite. And what we'll learn in this section is that when the area that is in question is infinite, we just say that the integral diverges. That's how you say that that area is infinite. But I can give you a very similar example. This is y equals 1 over x squared. The graph looks pretty similar. I could ask you how much area is there to the right of 1 underneath this curve. And you might be, by the same logic, think it must be infinite. I mean, it's kind of the same idea. I guess the blue curve gets close to 0 a little bit closer than the red, or a little bit faster than the red one does. But they both have the same behavior, that they have a horizontal asymptote at y equals 0. They both get infinitely close to 0 eventually. It'll turn out, and I'll show you how to calculate this, that there's infinitely much area below the red curve, but there's not infinitely much area below the blue curve, which is kind of strange and not obvious at all, and maybe somewhat counterintuitive. And so that's exactly the question we talk about with unbounded integrals. I want to show you how can you calculate how much area there is underneath the blue curve. Or how can you attempt to calculate how much area there is underneath the red curve and be able to state positively that there's infinitely much area underneath the red curve to the right of 1. So how do you do it? What if somebody asked you this question right here? The first thing we need is just to understand what this question's asking. And again, it's saying how much area is there underneath this curve to the right of 1, from 1 to infinity. And the way you could figure it out is be like, well, unfortunately, my evaluation theorem isn't going to work. Because my evaluation theorem only works if you read the fine print in your evaluation theorem when these are both numbers. And these are not both numbers, right? One of them is a concept, the concept of infinity, and then one of them is a number. But what we could say is that this is equal to the integral from 1 to b, where b is some constant, where it's a number, of 1 over x dx, as long as we're looking at the limit when b approaches infinity. So our first step is to be able to convince ourselves that these two integrals represent the same thing, because we're taking the limit as b approaches infinity. So this, it's a constant up here, but it's approaching infinity, so it kind of acts like this infinity right here. But the advantage to this form on the right over this form on the left is the form on the right is something that we can deal with using our evaluation theorem. Because if you just ignore the limit for a minute and focus on this integral, we can evaluate this integral. To evaluate this integral, we just use our evaluation theorem. We take the antiderivative of 1 over x, which is the natural log of the absolute value of x, and then we evaluate that thing from 1 up to b. And you're like, whoa, how do I evaluate it from 1 up to b? What is b? B is just a constant. It's just a symbol. All you were going to do is change all the x's into b's, and then change all the x's into 1, and then subtract those two things. So this is just the limit as b approaches infinity of, and again, we're just working inside the parentheses here, the natural log of b minus the natural log of 1. And you might argue that I need to put absolute value signs here, but since 1 is a positive number, the absolute value of 1 is just 1. And since b represents a positive constant, and you're like, wait, how do I know it represents a positive constant? Because I'm looking at the limit when b approaches infinity. So it's approaching some arbitrarily large number. So because it's positive as well, I can drop the absolute value notation. So what is this equal to? Well, the natural log of 1 is just 0. So this is the limit as b approaches infinity of the natural log of b. And then I ask you to evaluate this limit. And this goes all the way back to the first section we talked about in this class. We didn't hit on it really hard, so it's okay if you don't remember it. But when we were talking about limits, I think what I said is that natural log works in such a way that if the argument for this function gets arbitrarily large, then the value of the function itself gets arbitrarily large. What I'm saying is this limit approaches infinity. And maybe you can kind of convince yourself of that by looking at the graph, although it's not a super convincing argument. Here's the graph of y equals the natural log of x. And what I'm saying is if you go far enough out to the right, you can get as high up as you want to go. This is never bounded above. And I know it kind of looks like it's got some asymptote and it's going to stop, like it's never going to pass 2. Yeah, it is. You just have to go far enough out to the right. All right, here we go. We passed 2. Yeah, but it's never going to pass 4. Yeah, it will. It'll pass 4 or 5 or 100 or any other value you want. If you don't believe me, I can show you exactly where it would pass, 100. All I'd have to do is solve the equation 100 equals the natural log of x. If I could figure out what x would make this true, then I would know at what x value the height of this function passes 100. And to solve this equation, all I got to do is e to both sides of the equation. So whatever e raised up to the 100th power is the x value at which this graph's y value would pass 100. So it takes a really, really long time. This is some huge number, but the point is this is never bounded. The limit as b approaches infinity of the natural log of b goes off towards infinity. And the fact that this goes off towards infinity means that this integral right here that we were originally asked about is divergent. So you go through this work, you get infinity as your answer, and you just say that this integral is divergent. And you might be like, that's always going to happen, right? Because I'm going to be evaluating the limit as b approaches infinity. How could we ever make that not go off towards infinity? How could it ever not be divergent? Let me show you example number 2. Very similar to example 1, except instead of my function being 1 over x, it's 1 over x squared. Instead of looking for the area underneath the graph pictured in red, we're looking for the area underneath the graph pictured in blue. To the right of, let's pick on the same value, although it doesn't really matter where you start. Let's start at 1 here. Well, we can do the exact same trick, right? Our evaluation theorem won't let us figure this out, but it will let us figure out the integral from 1 to b of 1 over x squared dx. So we kind of cheat a little bit. We're like, yeah, the evaluation theorem doesn't work on infinities. Oh, no. Evaluation theorem. I would never ask you a question with infinities. Don't worry about it. I'm not going from 1 to infinity. I'm going from 1 to b. And then once the evaluation theorem gives me this answer and kind of the evaluation theorem leaves the room, I can then go and figure out the limit as b approaches infinity to sort of use that to figure out this. Antiderivative of 1 over x squared. Well, if you think about x squared as x to the negative 2 power, then the antiderivative of that would be x to the negative 1 power, except you're not quite done. We still have to multiply by the reciprocal of that new exponent, so 1 over negative 1 if you want. So we're looking at the limit as b approaches infinity of this expression evaluated from 1 to b. What happens when I plug numbers in here? Well, let's see. I'll first plug in b, so I'll have b to the negative 1 power. b to the negative 1 power is the same as 1 over b. So I'll have negative 1 over b because this coefficient is negative 1. And then from that, I want to subtract, and I plug in 1. 1 to the negative 1 power is the same as 1 over 1, which is just 1. But it's not just 1, it's 1 times this coefficient, which is negative. So I'm subtracting negative 1. So I got to evaluate this limit. Well, maybe if I clean this up a little bit, negative 1 is positive 1. So I can think about this as 1 minus this term, the 1 over b. And I think this is something that we can evaluate, right? The limit as b approaches infinity of this thing. Well, this fraction, when the denominator gets arbitrarily large, 1 over something that's infinitely large goes towards 0. So I get 1 minus 0, I get 1. That might be kind of surprising, right? That the area underneath this curve in blue to the right of this number 1 is exactly 1. I don't know. I don't see any reason why that should necessarily be the case other than calculus just showed us that it was. And there's nothing special about the two examples I just chose. I just wanted to pick one that was convergent. And if it's convergent, typically you use the phrase it converges to this answer, but I'm fine with you just writing it equals this answer. Either way is fine for me. And that's all you do when you have unbounded integrals. When you have unbounded integrals, you're either looking for the area underneath the curve to the right of some value or to the left of some value. There's no reason I couldn't figure out how much area there is underneath this curve from, I don't know, negative infinity up to negative 4 or something like that. You can be unbounded in either direction. It's totally fine. All you do is you replace the infinity or the negative infinity, whichever it happens to be, with a constant. And the standard is if the negative infinity is down here, you use the constant a. And when the infinity is up here, you use the constant b. Although it really doesn't matter. That's just the notation that most books use. So I can take the limit as a approaches negative infinity of a to, I don't know, negative 4 of 1 over x dx. And figure out what that is. It's going to turn out that's infinity as well. It's going to turn out that integral would also be divergent. So we could take whatever function we want and we could have it unbounded on either side, negative infinity or positive infinity. And all we're going to do is set it up the same way. We're evaluating some limit, either the limit as a approaches negative infinity or the limit as b approaches infinity, of some integral. And the integral will either have an a here and a number here, or a number here and a b here. And all you'll have to do is take an antiderivative and use your evaluation theorem, and then that will leave you with a limit. And how do you evaluate this limit? Well, it kind of depends on what your function is here, right? Sometimes it's just something you can evaluate by looking at it, like it sort of was in these two cases. But maybe if I pick a function really cleverly, this limit would involve, I don't know, L'Hopital's rule maybe. But it shouldn't be any limits that you didn't learn how to evaluate in 2.5 and 4.5 in the first couple weeks of this class. And that's the idea with unbounded integrals.